evening, everyone. I am Suraj Borate, a PhD student from IIT Gandhinagar, and I am joined by Bhavish Rai B and Vipul Pardeshi right here. Say hi. Okay. So we are here to introduce you to our open source collaborative multi-robot system ROS2 package, CoMuRoS. So what does this do? So these are the objectives. Our package provides a framework for task planning and execution for multi-robot collaboration. And it provides a seamless, anytime, natural language, human-robot communication. So you can communicate with your robots, multiple robots at the same time in natural language, something like this. So here in the first video, hello, yeah. In the first video, you can see there are 3 robots. There are 2 robotic arms, one near the patient, one on the table, and there is a quadruped robot nearby. Let's say the human types in this interface or says out loud, I am hungry, right? Then our system plans which robot should do what and delivers the food autonomously. It plans autonomously and delivers the food autonomously to the patient, right? This is what I mean by the first 2 points. Then it has one really cool feature called adaptive replanning, right? So what adaptive replanning means, it understands the meaning of events that take place in the environment, and if required, there is a change of plan, right? If there is a change of goal or there is some problem is there, then automatically there is a change of plan, something like this. The quadruped was going to deliver the food, and human said, I don't want it anymore, in real time, right? So in the real time, there is a replanning, and the quadruped goes back to the home position. The most important feature is that this is a generalized architecture. So this is not limited to these videos or the hospital environment. You can do your own custom applications with this. So now that I talked about generalization, let me go back into some thoughts that were put into, or the ideology behind building intelligent agents in general. So intelligent agent should have at least these 4 aspects, or utopian intelligent agent should have these 4 aspects at least. One is the behaviors. Behavior means the skills, right? The robots or your agent should have skills like let's say cycling, running, walking, pick and place, right? And these skills can be based on your classical control algorithms or reinforcement learning algorithms, pre-learned policies, or VLAs, physical intelligence, right? Then agent should have thinking capability, planning capability, coming up with solutions to problems, right? We all think in natural language, right? Most of the time we think in natural language. So this we can do using LLMs, the deliberative thinking part on the top, and to execute a plan or to form a plan, first we should understand the environment, right? We should understand the concepts like space, time. We should have general knowledge. Let's say you say that, okay, bring me a fruit that is rich in vitamin C, right? So it should have some general knowledge. Sometimes it may need some domain specific knowledge. It should understand the meaning of stuff around, right? That also today is well provided by the foundation models, right? There are some problems with multi-sensor or multimodal things, but those are coming up with the building data sets that was discussed earlier, right? But the most challenging part is the learning part. Then this is different from the reinforcement learning and VLAs and the physical intelligence, right? This is largely unsolved part. Can you guess what is that? This? So this is like learning like humans do, right? In reinforcement learning, to learn a certain skill, how many times the agent dies, right? Whereas a human being, if say I want to learn cooking, right? How many times maximum you think I will burn myself or I will get killed before I learn cooking, right? So human beings has the ability to learn new stuff while being deployed in the environment, right? Unlike robots, right? So learning while being deployed, learning to learn, we improve our way of learning, we improve the current knowledge also, right? We improve our planning capabilities, we improve our policies without turning off ourselves, right? Without getting into अभी मैं खुद को train कर रहा हूँ, बाद में मैं खुद को deploy करूँगा, right? So, but this is a largely unsolved problem. But the good news is that with the top three circles, the current knowledge, deliberation capabilities, and the behaviors, we can still do a lot of cool stuff, right? And there's a lot of regret. Like, okay, India has missed the LLM revolution. India also missed the AI revolution. India missed the electronics revolution. But yes, there is one revolution that is yet to come. That is the dynamic learning or the continual or the lifelong learning, this thing. And I think here there is still a lot of opportunity. This is the future. I don't know when it will come. Okay, but right now let's focus on the current knowledge, the behaviors using RL, VLA, or the classical things, and the deliberation. Okay. So coming back to our application. Now our application is a multi-robot application. So we have multiple intelligent agents and we have a multi-agent manager agent. Okay. So the multi-agent manager agent will interact with the team of robots and humans, and this entire setup will interact with the user. Okay. The user hopefully for now is a human intelligent agent. Okay. So as you can see, the manager assigns tasks to the employees based on their skills, right? There is the task allocation function that we are inspired from. Second is the employees. They, in a decentralized fashion, they understand their skills better, so they use their intelligence and execute the skills. And then whenever there is an issue or any update, they communicate with the manager, right? Then another inspiration is that we perform coordinated tasks. We perform tasks independently. So one of them can drive JCB, another is picking up the piece. And we perform tasks sequentially. So we understand task classification. So how to coordinate, okay, and what type of coordination is required. And the last but not the least, we have the ability to replan. So, for example, when something goes wrong, still the show must go on. We find an alternative plan to do it. And when we have multiple agents, if someone has the capability to help us, then we collaborate with that person. Now let's bring that to the robots. But before that, let's compare our architecture with the state of the art in the recent times. So from 2024 to 2025, these are the multi-robot architectures, and ours is the last column. And we see that we have a unique features of generalization, event-driven replanning, and ours is a completely open source ROS2 framework. And we have demonstrated all this in hardware demos. This is, you can take the photo. This is our research paper. You can scan for the research paper. I'll wait for 3 seconds. Okay, let's go to the architecture. On the left side, you can see the task planner. The task planner has the capability of task allocation, task classifier, and task replanner. It receives the task through the human interface, where the human can communicate, change of plans, interruptions, feedback, etc. in natural language. And it can also monitor all the plans in the interface and all the history of the conversation, right? That is an important context. That is taken as a context by the task manager. The task manager is basically an LLM. And on the right, you can see one of the robots. And each robot has a LLM Python code generator for execution. So all the code, execution code is generated by this LLM based on the high level tasks provided by the task manager, right? And it utilizes the list of skills. These list of skills can be your RL policies, VLA policies and all, okay? And then there are, it proactively communicates any events that based on its sensors, because it has knowledge of the task of all the robots and what is happening. It communicates, it classifies and communicates the event if it is relevant to the task to the task replanner, and the replanner replans. Okay, so here is the core task manager logic. The task manager logic is purposely divided into a static section and a dynamic section. So static section means that this is task agnostic, right? It will not change. That is the intelligence behind the multi-robot collaboration, right? It contains all the definitions of what is a sequential task, what is task classification, how to do human collaboration, and all that stuff. Okay, and then there is a dynamic prompt. Okay, in the dynamic prompt, here you can customize, right? Here you can customize to your scenario. Here you can give the commands. Here everything is there that changes with time, right? So this file, configuration file, scenario configuration file, will contain your list of robots, your capabilities of the robots, and the constraints of your robots. Okay, so this is a chat interface. We also have now voice communication, but this one is the old version. You can type in the commands and you can see your commands. You can see which robot should do what, the plans, and also the proactive reporting of events by the individual robots in one place. Okay, let's go on to some of the experimental results. So this is the first experiment that demonstrates replanning and adaptive collaboration. Here we have 3 robots. One is a mobile manipulator, Waffle, burger robot equipped with camera, and a quadruped which has a green object on its back. Now the user asks Waffle to go to the bottle, and quadruped to carry the green object to some particular location. And what will happen if some human being comes and throws the green object away, right? Let's see. Yeah, I started. Okay, so the command was typed in the chat interface. All the sensing is happening on board, right? So I throw the green object away, and then a replan was generated. It identifies that according to the capabilities of the robot, only Waffle robot can help the quadruped, right? And the quadruped sits down because it understands the constraints of the reachability of the arm of the Waffle robot. And after helping the quadruped, the Waffle robot remembers that it has to go back to doing its original task. And this all was done autonomously without any programming, right? So we observed that there is an emergent collaboration resulting robots helping each other and resumption of incomplete tasks in this experiment. And this experiment gave a success rate of 9 out of 10. Now let's see the next experiment. Here we have a formation of robots and a robotic arm, and the task is deliver the ball to a particular location. A plan was generated where, and the context was given, right, about the environment. There is a table and there is a catch point, etc. The formation goes to the catch point. The ball is pushed into a box, and then formation delivers. Okay. Let's say if the ball falls outside, right? What should happen? Was the initial plan? and the ball falls outside. And this event was detected using a VLM, right? That this can affect the task. And what what happened is, forward it. Let it rerun once. So what happened was the replanner identified that none of the robots can help in this situation, and it summoned a human being to help the robots. And the human being came and placed the please manually place the blue ball into the box. The human being placed the ball. This was also detected by the VLM, and then again replanning took place. It said that okay, you can deliver the ball to the goal position. It was done with success rate of 5,5, 5 out of 5. And we can see that when a task or situation is outside the capability of the robot, right, then still the show must go on, right? If something wrong happens, then human can come and intervene. So there is a human-robot collaboration. And now we can make a better sense of the entire chat history that I had shown earlier. In the interest of time, I will skip this. So we also wanted to test our architecture. So we created a textual dataset of over 22 scenarios and 3 tasks each, and we evaluated it 5 times over 10 different LLMs. For this metrics, I will not go into the details of the metrics, those are available in the paper. First one we can see, that is correctness, whether the plan can achieve the desired outcome as judged by a human. Okay, so across these 10 different LLMs, from API-based to offline models, we observed that Grok 3 had performed better than others with a success rate of 91%. And this is another testing where we see the robustness to different phrasing of the commands. Okay, so now the fun part, how to adapt CoMuRoS for your custom scenario. So here is a toy example. Let's say you have a food court. Okay, let's consider a food court, and there are 3 stalls. One provides veg food, one provides non-veg food, and one provides cold drinks. And we have 3 robots, a delivery bot, a drone, and a cleaning robot. Right? Now what to do? How to use our architecture? Just in case, all the code and this tutorial is open source and available at this website. You can scan or take photos. It is available in ROS 2 Humble, 22, Ubuntu, and Ignition Fortress based simulations. Okay, so there are minimal changes that you have to do. As we had discussed earlier, to the configuration file, you just mention your robot names, the capabilities of robot. For example, drone is positioned at a place above the food court. Its primary job is to answer the questions about the scene using an VLM. Delivery bot has to deliver items from stalls to table, etc. Then your task specific rules. It's your restaurant, your rules, which stalls provide what, and other stuff. You can tweak this. You need to tune little bit. But yes, as we have seen, every bot has an LLM brain. So you have to and a skill list. Those skills can be anything, RL policies, VLAs, or classical control, PID and all. So you have a dictionary with each LLM where you describe the skill in natural language and provide the API function for that. That function can call your VLAs or RL policies or your PID controllers and all. Right? And VLM integration. So for example, here, this is a very simple example. And for this, the VLM prompt is, your job is to analyze the image from drone's bottom camera and answer the user's question or task manager's question. So let's see what happens. So in natural language, you just say that serve salad to the child. Then using the concepts and the common sense of the LLM, it understands that, okay, salad is veg, right? I have to go to the stall number 1, right? And it plans accordingly. But then it says that, okay, to the child. We didn't say like where the child is placed, right? So it asks the drone, identify the location of the child. So Ron replies using VLM. The child is seated at table number 2. Sorry, we didn't have time to place the arm, but arm you have seen in the hardware. So next is clear the table. Not mention which table, but okay, English language. So okay, clear the table. Table food is only on one table, right? And then it goes to the sink, right? Okay, on the interest of time, I will skip the second demo. In conclusion, I will say that the features provided by the package are human-robot collaboration, multi-robot collaboration, right? Robots helping each other, event-driven replanning, and most importantly, generalizable and customizable to your scenario, right? The future work we are planning semantic navigation layer. You can also contribute to our repo. Dealing with unrecoverable situations. Like sometimes the situations are not recoverable. Then what to do, right? It's not the end of the world. What you should do, right? Performing partial completions, right? And lots more. Okay, thank you. This was our small contribution. I need one help from you. Please share your valuable feedback on this QR code. Each one of you, please. And this you can connect with us on LinkedIn at that QR code. Thank you so much.